This side's just fine.
Would you ask me if you needed intro micro for patho? I don't think so.
Okay. I'll double check, but I might think that.
I think they're separate.
Be excited.
Every time
All right.
you
Exciting night last night, right? I didn't see it. Didn't watch it.
I mean, I can set a dumpster on fire. You get the idea.
That's
pretty much what it was.
Yeah.
Yeah. I didn't watch it. Didn't worry about it. I knew it was on. Then when it was over, I didn't even want to watch the news. I didn't want to hear the news. I said, you know what? Heck with it. So I started trying to get caught up on Deadliest Catch. That's what I was doing.
Yeah. Probably less.
All right. So yeah, it had been so long since I had watched the last episode that I wasn't sure if I actually saw it or not. So I started rewatching the one that I had already watched. And it was probably, I don't know, 10 or 15 minutes when I said, oh yeah, I remember what happens. Still trying to get caught up. All right, so we have here quiz. No, not quiz. Homework was posted. I'm glad I didn't watch it. Anyways, we got homework posted. So I did homework 4. That's the one that I'm gonna ask that it's due today, and I'll ask you if you have questions. We can go over those now. Homework 5 and homework 6 is also posted. I haven't assigned due dates, but homework 5 and homework 6 is just a repeat of binomial distributions and Poisson distributions. We haven't talked about Poissons. We'll talk about those today and probably finish those up on Friday. So once we finish it up, then we'll assign those homework assignments. I am going to put together a quiz on probability. All right, so homework was due. You can kind of review that, and it'll be a Blackboard quiz. So I'll ask you calculate the probability of this event, and it'll probably be fill in the blank. We'll see. I have to make it up. That's going to give you practice. There will be at least 1, possibly 2 Bayesian probabilities. So with those Bayesian probabilities, what I generally do is I ask you to calculate. Tell me what sensitivity is or specificity. If maybe I give you a false positive, false negative rate, then I might ask, what's the sensitivity, specificity, and then I'll ask like, what's the probability that we'll get a positive test, and then if the test comes back positive, what's the chance that you actually have it? That way, it kind of steps through it, and I know this is going to be harder with the online versions because in the paper versions, I can track if you flipped, let's say, sensitivity and specificity values. If you thought they went into the wrong spot of the table, then those numbers carried forward. That meant that your answers are all going to be wrong from that point forward. So it was pretty easy when we had it on paper where I could see the work and say, oh yeah, this is why your numbers are off. You put this in the wrong place. And then you just lose points for not knowing what sensitivity specificity was. You didn't lose the points for not knowing how to actually do it, right? So that's going to be kind of the hard part here, that we can't really track that. We can't make sure that you follow along in the correct spot. All right, so homework number 4, probability stuff. Any questions on that? Any questions on homework number 4? Hopefully it's straightforward. proceed. So, asked you to do this, have this done. We'll go over it. And so first up, we have to convert our table to a vector. And we need to do that because we have to get this P. We have to get the probability of success. In order to get the probability of success, we have to get the average number of males per clutch. That average number of males per clutch is this mu here. This would be x bar, since we're dealing with the sample. All right, and then from x bar, we divide it by the total number of possible males in a clutch, or clutch size, in this case 7, to get that P. So we have to somehow get our data into R to calculate that average. And the easiest way to do it is to convert it to a vector. So what I'm going to do is show you get this up here. Instead, I don't want to. This RStudio is going to cover it up. Right, and all right, so here's mine. So going to convert a table to a vector. This time I went ahead and made my males, a vector of males, so 0 to 7. That's that X category. I called my frequency column W. All right, so just another way to do it, just kind of reinforcing where these things go. And then I make my clutches vector, which is to repeat the male vector W times. And again, just as a reminder, this 0 to 7 gives me a 0, 1, 2, 3, 4, and then as we do the rep, it goes basically row by row in our vector. So I'm going to run this chunk, get my clutches vector, and then our average number of males ends up being just the mean of our clutches vector. So 2.82. 2.82. So then we can get probability of being male. Get this is the mean of our clutches divided by 7. So we said maximum we can have is 7. Our clutch size is always going to be 7 in this case. So mean of our clutches is out of 7, which gives us a probability of being male 0.4028571. All right, so we have that information. What we now need to do is to get this information. So the given data, we need the probability, and then we need the expected. If we were doing it by hand, we would use our calculator, but we're just going to use R now. So let's get our probability. So what function did we use? D binom, right? So D binom is our probability. It's our density. You can remember density because we'll come back to that for continuous distributions. So D binom, we need to know 0 to 7. All right. Our probability 0 to 7, our size. So the out of number is 7, right? And then we have our probability of success. So our probability of success is that number there. And what I will do is just take mean of my clutches divided by 7. So instead of actually typing in the number, I'm going to use the function because, again, R can do that. I didn't have to go through all of this one by one to get those numbers. I can just pass all of those numbers right to here, and the mean of the clutches divided by 7 will report that number. And not only that, it won't round it. So this number here represents a rounded number. So when I run this, now I get all of my probabilities, right? And I can go through and manually round them if I wanted to, or we can actually do it ourselves. So round, we'll say 3 decimal places. Probably sounds about right. And it reports my 3 decimal places for me. Less brain power. So that's our first column. That's that PX column, given the data. And it was given the data because we had to calculate P of success, probability of success, or probability of being male. And then the next thing we need to do is get our numbers. All right, so I'm going to copy this D binom. And I'm going to paste it. So that's our probabilities. And we get our expected number by multiplying the total number of clutches that we counted. All right. What was that total number? So I'm going to do length of clutches here. All right. This is one way to do it. Since I made that frequency vector and I called it W, I could have also done like the sum of that W vector. It gives me how many rows I have in clutches, and the length gives me my sample size. That's the number of rows in clutches and so forth. So then when I run that, you will see that I get actual expected counts. Now, again, these are full numbers, rounded to decimal places. If I want whole numbers, I can do it manually, when I write it in, or I can let R round for me. So 4 and 19, 39, 44, 29, and so forth. All right. So then what we could do, one of the applications of this, is to look at these numbers, 4, 19, 39, 44, 29, 3, and 0, and compare them to what we actually see. So you can see that it's basically identical, right? Which I'm going to say kind of surprising, but then again, it's not. And I say it's not because I generated these data randomly. All right. So it kind of demonstrates that, yeah, we saw what we actually, expected. I should say the number of males in a clutch appears to be random because it follows a binomial distribution. That's what we get. That's what we expect from a binomial distribution. All right. Now we're not going to see that for the second part. So the second part was, what if we expected 5 males per clutch? Let's say we did this some other time or some other location, and we saw an average of 5 males per clutch. How do we do that? All right. So how do we do that? Well, we're going to basically do the same thing, except we are going to update what our probability of success is. So I'm going to do these all in one line, or one chunk. So I'm just going to copy and paste what we already have. We know it works. All right, we're getting the values that we needed to. But the difference is where is this prob? We have to change that. So instead of taking the mean of the clutches, we have to take 5. And we still have to take 7 divided by 7 because we need to calculate the probability of being male. So I'm going to replace the mean of that clutches there with 5 because that was given to us in our problem. That was given to us. And I'm going to round as well. Just leave the rounds and stuff. So then when I run it, I get my values right there. I can enter them into a table. If I was using this table in a paper or something like that, or a poster, I'd make that table in Excel, remember? And then I'd copy and paste the Excel document into PowerPoint or whichever program you're using to make the poster. All right. So this is our expected values. It's our expected counts. And if we go back to what we observe, our expected counts are quite different. Right? Our expected counts are quite different. So we had most of our distribution, most of our values fall in this 2 to 3 range, closer to 3. Whereas our expectation, most of them were going to fall in this 5 range. All right. So right now, if we look at what we actually observed and compared it to what we were expecting with an average of 5 males per clutch, we're starting to see, yeah, that our data doesn't really match what we expect. Visually, it doesn't look like it matches what we expect. But we would need some sort of statistical test to kind of demonstrate that, yeah, this isn't just a random chance event. You know, something other than chance produces these differences. Any questions? So hopefully you did that. It's not too bad when you have D-binom and you know how to use it. It actually comes out pretty quickly and pretty easy, pretty fast. Right? Doing it on a calculator adds some time. Definitely add some time. Where's my cursor? Here it is. All right, so the binomial distribution was modeling events, dichotomous events. So success, failures, true, false. All right? And it modeled the probability of that event happening out of some total. All right? Poisson also models a dichotomous event. You know, success, failures, male, female, presence, absence. But we don't have an out of number. All right? It's assumed that we can have an infinite number of possibilities that take place. All right? And that thus means it changes our distribution. Now, what's kind of interesting is that the Poisson approximates this binomial distribution when our probability of the event is rare. Okay, so our probability of success is less than 10%, and our n times p is less than 5, when our average value is less than 5. Right? So when we have those two conditions, then the Poisson distribution will actually approximate a binomial distribution. But if we don't meet those requirements, then our Poisson distribution is the Poisson. When do we use this? Well, if we look at the probability of the event itself, and when we look at that average, what you'll see is that these events, Poisson distribution, is usually used to model these rare events. And rare events that happen. It's like, a lightning strike, right? Or time between lightning strikes. That's a Poisson event. Right? That's a Poisson distribution. It's Poisson distribution because it's a small probability of things happening. Right? Probability of success is low. Right? But also, we don't ever have like a finite sample size. It's assumed to be unlimited. So that kind of goes hand in hand. If we have an unlimited sample size or an unlimited out of number, then by definition, our probability of success is going to be rare. So here's an example. This phone, it's been up here. Right? It's been up here since, since I started here working, in this lab. Right? We can ask, what's the probability that this phone is going to ring? All right? And we can ask, what's the probability that it's going to ring 2 times? Did I give a time span? No. So we have this situation where it might never ring, right? Or it could ring in the next 5 minutes. That's a Poisson event. That's a Poisson event. All right. When do we use it in biology? 2 cases. Spatial distributions, temporal distributions. So temporal distribution would be the time, how many seconds elapse between lightning strikes? How many seconds elapse between, phone calls? Right? How many at-bats happened between home runs in a baseball game? All right? Those are temporal distribution events. Spatial distribution is spatial distribution across the landscape. Distribution of individuals across the landscape. That follows a Poisson distribution. All right. Now, on all of these things, we use this distribution because the distribution models a random and independent events. All right. It models random and independent events. If our actual distribution, if our actual dispersion of individuals does not follow the Poisson, then we can conclude that no, this is not random and independent. Something other than chance is affecting those distributions. So here's an example. All right, here's more explanation. So we need our average to be less than the maximum, right? And that thus means that it's going to be a rare event. So if we looked at trees in a grid, right, in theory, our grid should be able to hold an infinitely large number of trees. Now that's going to be kind of unrealistic if we set up a grid that's the size of this room and put it out on, across campus. Yeah, you can't fit infinite number of trees in this space, but it should be sufficiently large that we don't ever approach that number. So we're not going to set up, a grid of 1 meter by 1 meter square and go out there and count tree distributions, because that grid, what's it going to hold? Maximum 1, 2 trees, if that. All right, that's not a sufficiently large number of trees. So as we do these, we have to set up a sufficient size to where our average value is going to be much less than the maximum, right? But at the same time, we don't want it so large that it becomes unrealistic to try to survey and try to collect the data. The other thing is that the occurrence of our events must be independent of all of the other occurrences. So we can't have a situation where if this phone rings, it's going to be more likely that it's going to ring again. All right, we can't have that happen. Each of the events has to be independent. Now, you can say that sometimes home runs kind of run in groups. Maybe it is, maybe it isn't. But if we look at the bigger picture, the chance that I hit a home run is going to be independent of the chance that Nate hits a home run. Usually. All right, we can kind of get into sports psychology and motivation and all that stuff. We'll leave that for other departments. But for us, we assume that the events are independent of prior occurrences. Do we ever follow that? Do we see that in nature? So if we said, let's say, distribution of trees or plants across the landscape, is their presence independent of each other? Alex shakes his head no. Why do you say no?
Because trees tend to grow in communities. Like above a certain elevation, you'll find mostly aspen.
Okay.
So are you talking about trees in general or certain species?
No, you can say trees in general. That's okay. So sometimes they do. Sometimes they are independent. Sometimes they're not. And when they're not independent, there are things like what Alex said. Trees tend to prefer the same types of environments, same types of conditions. So if we go at the micro scale, the soils are going to differ in their nutrient concentration and their water concentration. And if it's a favorable environment, you're probably more likely to find more trees in that area than if it's not. So that's kind of the whole basis of why we compare our actual distributions to Poisson distribution, because Poissons assume that everything is random and independent. All right? So if we use a Poisson distribution to look at these spatial dispersion patterns or temporal dispersion patterns, if our observed matches what we would predict from the Poisson distribution, then our data are randomly distributed. Our individuals are randomly distributed. If the presence of one individual increases the presence of another for some reason, then we would say our distribution is clumped. All right? If the presence of one decreases the presence of the other, then distribution is uniform. And kind of have that example. So what we often see in nature is something like this. Think about social organisms, or organisms in general that socialize. This is what we tend to see. They tend to group together. Right? Why do they group together? Any number of reasons. But this is not a Poisson distribution. And comparing this distribution to a Poisson distribution would reveal the pattern. It would tell us our data are clumped. Right? We also have this other case where everything is uniform. So basically individuals are uniformly spaced. Right? That is a case where you probably have negative interactions between individuals, where the presence of one prevents others from getting close, getting nearby. Now, we compare this to a Poisson distribution, and we'll learn how to do goodness of fit tests to make that determination. But there's another way in which we can kind of make a quick classification as to whether or not a distribution is clumped, random, or uniform. How do we do that? We compare the variance, and the mean values. All right, so if we compare it to a Poisson distribution, right, we look at the variance of the distances between individuals. If we are clumped, so the Poisson is our sigma here, all right, S is our actual sample. So we have a bunch of small values, a bunch of close values, and then each of these is far from all the other ones. So that leads to a sample variance that's going to be larger, much larger than a variance predicted by a Poisson distribution. You get more dispersion than what's expected. If we're clumped or uniform, all of our variances, the distances between individuals, are all going to be very similar. All right, which means the overall variation in those distances is going to be much less than what would have been predicted by the Poisson. All right, and what we'll get to is that with this Poisson distribution, it's defined by the mean. It's defined by the average value, the average number of presents, or whatever. And what's kind of interesting is that the mean and the variance are equal for a Poisson. And we will use that. So here's our Poisson distribution. All right. This is our equation. It's calculated by taking lambda raised to the x divided by x factorial e to the lambda. What are all of these? What we're trying to model is what's the probability of getting x successes. We didn't say an out of number. We just said what's the probability of getting x successes. All right. And we have lambda. Lambda is the mean number of events per sampling period or unit. So again, we didn't say an out of, we just said, okay, the average number of successes that we get is, let's say, 2. All right, that's our average. And then we say, well, what's the probability that we'll see 5? Well, we didn't set up a fixed time. We just said, what's the probability we're going to get 5 of these? So we use 2, that's our average. We're going to raise it to 5 because that's the number of successes that we're looking for. All right, and then it's going to be divided by 5 factorial, e to the lambda. I can show you how to do it on the board. It's actually pretty easy. And it's pretty easy to do it sequentially to get that 0, the 1, the 2, the 3, the 4 measure and not do this entire thing over and over and over again, because what we do is just multiply by lambda and divide by our next x. E to the lambda is a fixed value. That doesn't change. So once you do it once, that's it. Are we going to do it by hand? Nope, we're going to use R. Whoops. And our function in R is dPois. So we saw a dbinom, that's our binomial distribution. And for the Poisson, it's dPois. D-P-O-I-S. All right. We give it our x value, so the number of successes, and then we also give it our lambda value. So again, note, just drive it home, hopefully. We don't specify a total sample size. We don't specify a total sample size. However, when we report averages, the expected numbers, we do use some sort of sample size. So trees in a grid. We've dropped a grid. We will have an average number of trees observed in a grid. All right, so that's our sample size, you can say. All right, so I give a chicken example. So we infect 10 chickens with H5N1 influenza, so that's a high-path influenza virus. All right, and then we record the day of death. All right, we didn't record if it died or not. We recorded when it died, right? It's possible that the chickens never die. So that day of death becomes basically infinite, or until it hits its end of its lifespan, right? In some cases, it may die on day 1, may die on day 5, but we don't ever have that out of number because that individual might never die. So let's do some example here, right? So chickens. This time we infected 20 chickens, right? We've got our day of death. So you can see that all 20 chickens died in this case, all right? So what we want to do is calculate probability of death and the expected numbers of death on each of the days, all right? So we'll start with getting these data into a vector so we can calculate our average. Okay, so we can see all that. Great. So go ahead, convert these data to a vector and calculate the average. Get it? That over. So chicken example kind of show you how to do it. So you've got our day, made it vector of days. So 0 to 4, our numbers, that was in our table. I called my vector CK, chicken. All right, and then mean day of death is just the mean of that. All right, so in the binomial distribution, we divide it by our total sample size, right? Our total out of number to get that probability of success. In a Poisson, we don't have that. We don't have a separate probability. We use the average. We use this value. This is lambda. All right, so mean day of death equals lambda. All right, so now we need to calculate the probabilities. So we're going to do P of 1, or 0, P of 1, P of 2, P of 3, and P of 4. All right, that's what we're going to calculate. And I wrote them out like this just to kind of emphasize that, again, we don't have an out of number. We're not asking P of 0 males out of 7 or P of 1 male out of 7. This is just flat out P of 0, P of 1, P of 2. And then I'm going to use my dPoise. All right, so dPoise is our density of the Poisson distribution. All right, it needs our x values. So we're going to go 0 to 4. And now our lambda is equal to the mean of that vector, 1.3. And when I calculate that, when I run it, I get my probabilities. And what we should see when we have these probabilities, our mean is 1.3. Our highest probability should be around that, whatever that mean is, that 1.3. expected values, we do the same thing. I am going to copy and paste. And we had 20 chickens. That's what we were working with. So on day 0, we expect 5 chickens die. Day 2, we expect 7 chickens to die. Day 3, we expect 4.6 chickens to die. Day 3, we expect 2, and day 4, we expect half of the chicken. Now again, we can't have halves, you can't have decimals, so you can do round whole numbers to get to that. It's probably what I would recommend. So I will round, and I'm going to round to a whole number, so 0, and that's better. So 5, 7, 5, 2, 1. That's what we expect. Oh, crud. There it is. That's better. Slide that over. All right, so we have our expected values. Now we can compare them. So we know what we expect from a Poisson distribution. This is assuming that day of death is a random event. All right? Day of death is a random event which would follow this Poisson distribution. We can see that we expected 5 chickens to die on day 0, but we actually saw 3. All right? We expected 7 to die on day 1, but we saw 9. We expected 5 to die on day 2, but we saw 7. We expected 2 to die on day 1. We only saw 1. Then we expected 1 to die on day 4. We saw 0. All right, I'm not so worried about that last day, but I am concerned about this. We have a lot more happening on that 1 to 2 days than what we would have expected by chance alone. All right, is this perhaps random? Is this perhaps just a random chance event that if we repeated it, we get a slightly different numbers and we're more like the Poisson? Yeah, it's possible. That's why we would have to do some sort of goodness of fit test to kind of assess how likely is it that we would actually observe these numbers if we actually do follow a Poisson distribution. That's where our goodness of fit tests come into play. Now, does this look like we're clumped or repulsed? So if we're repulsed, then we should be evenly distributed, evenly spaced out. And clumping, here's the idea with clumping, is that we should have more values of zeros and more of the upper ones than what we expect to chance, and less of the ones in the middle. Right now, I don't think that's the case. I think we are more uniform. The uniform's the opposite. We have more in the middle than what we expect, and less at the extremes. And we'll see some of that. Any questions on this? So our Poisson distribution is defined by the mean. All right. An interesting thing with Poisson distribution is that the mean and the variance are equal. All right. The mean and the variances are equal. So as we increase our mean, our curves move to the right. That reflects our average, right? Increase in our average, and also the curves widen out. They get wider because as the average increases, so does the variance. All right. So what you get are these different curves, or what you can get are the different curves, and those different curves are going to be defined by the different lambdas. So in theory, we can have an infinite number of curves, just like in the Poisson or the binomial distribution. You can have an infinite number of curves. Just based on the underlying parameters. Can we utilize this information here, the lambda and the sigma, or I should say the mu and the sigma? Yeah, we can, and it's something called the coefficient of dispersion. This is kind of like a rough estimate that tells us how our values are dispersed. Are they clumped, are they random, or are they uniform? All right, so the coefficient of dispersion is simply the variance to mean ratio. That's all it is. Take the variance of your data set, you divide it by the mean. If they're 1, the variance to mean ratio is 1, then it looks to be randomly distributed. It matches what we would have expected from a Poisson distribution. If our coefficient of dispersion is greater than 1, then we are clumped or aggregated. We've got a much larger variance than we have the mean, and the reason is we're comparing the average distance between each of our data points, but we've got some distances that are really small and then some distances that are really large. All right, so you got a large variance relative to the mean. If our coefficient of dispersion is less than 1, then we're uniform or repulsed, which means our average is going to be one value, and there's very little difference from that average across the board, so our variances are going to be pretty small. Do we ever just calculate the coefficient of dispersion and then make the claim, oh yeah, it's clumped, or yeah, it's uniform? No, we don't. What we always do is we get our values, we get our table here, we do a goodness of fit test to first see if it follows a random distribution. If it doesn't, if we can say, yes, this is not a Poisson distribution, then what we normally do is go this coefficient of dispersion and decide, okay, well, if it's not randomly distributed, if it's not a Poisson, then does it look like we're clumped or does it look like we're uniform? All right, so here's what we're going to do. We have a practice Poisson distribution. All right, just like we did on Monday, what I'm going to ask that you do is generate P of X and the E of X column under 2 different situations. So that's first situation is given the data. So you're going to have to calculate your average and then generate these columns. And then the second part is, say we assumed, or maybe in some other place or time, we measured an average of 3. We want to generate our P of X and E of X columns so that we can compare these grid data to what we would expect if the average was actually 3. So I'm going to ask that you do that and have that on Friday. And what we'll do on Friday is look at these numbers. I'll show you how I did it in RStudio, and we'll compare our checks. Just like the binomial, these are discrete distributions. So when you get to the expected column, it probably makes sense to use whole numbers, to round to whole numbers. All right. And that is it for today. And I know that we are ahead. That's a good thing. Good. That means we'll get to our confidence intervals next week. And we'll actually have at least a day maybe to practice confidence intervals before the exam. All right, so you have this ready to go on Friday. Y'all have a good one.